Welcome to the lecture number 32, that is voltage stability analysis. So already in the last class we discussed the voltage stability analysis, the introduction. So today we will discuss little deeply what is voltage stability analysis and how we can go ahead. So voltage stability analysis is nothing but it is the ability of the system to maintain the voltage within the limit even if there is some disturbance in the system. The basic concepts already we discussed in the last class. Let us review that same concepts. To understand the concept of voltage stability, let there be a two-bus system with one end being sending end and the other being the receiving end, as shown in this figure. You can see here this Vs is nothing but the sending end voltage which we have considered as reference, and here this Vr is your receiving end voltage, and Zt is the impedance of the transmission line, and Zl is the impedance of the load here. So we can see here so here we have considered Vs as the reference. So the magnitude of current in the transmission line, we can write it as I can write it as Vs by Zt theta t plus Zl phi L, the magnitude of that, that is the mod of that. So I can write it as Vs by this. Vs is the magnitude of the sending end voltage, and the magnitude of Zt plus Zl is Zt square plus Zl square plus 2Zt Zl cos theta t minus phi L. So this is easy to understand. The receiving end voltage magnitude is then defined as receiving end voltage. I can write as the current into ZL, that is the load impedance. So current is Vs by Zt square Zl square plus 2Zt Zl cos theta t minus phi L square root into Zl. So that gives us Vr. The real and reactive power also can be written from current expression, using the current expression, because we know that PL is equal to I square R. So R is nothing but ZL cos phi L. This is RL. So RL multiplied with I square, that will give us PL. And similarly QL, reactive power, also can be defined or can be written as current square into XL. So XL is nothing but ZL sin phi L. So in fact these two expressions plays very important role when we draw the PV characteristic or QV characteristic. So let the transmission line impedance be taken as Zt, that is equal to 0.25. Considering this Zt equal to 0.25 per unit, neglecting the resistance, as usually the reactance to resistance ratio is quite high in a transmission network. Let the sending end voltage be 1 per unit. The real and reactive power of the load can be increased obviously by decreasing the load impedance ZL and maintaining a constant power factor, say 0.8. So the receiving end voltage is plotted in the figure shown below with varying real power consumed by the load. So varying real power load means if we want to increase the real power load, we have to decrease ZL. So by decreasing ZL, we'll plot the receiving end voltage versus PL. So at that point, when we'll decrease the ZL, we'll calculate both the PL and VR. Then we'll plot it. So this curve is called as PV curve. So this is shown the typical PV curve. We can see here. This is the knee point. So from where, even if after decreasing ZL, we found that the PL is also decreasing and VR also decreasing. So this point is known as critical point or knee point or collapse point, voltage collapse point sometime. So it can be observed from the PV curve that there are that as the load increases from no load condition, the receiving end starts dropping from the initial no load voltage of 1 per unit. So the receiving end voltage start dropping in this phase. You can see here it gradually drops. Though the receiving end voltage drops, simultaneously the load power or the PL is increasing. You can see here the PL is increasing, but the receiving end voltage is decreasing. So the increase in the current I due to, so in this region from the beginning, from VR equal to 1 per unit to this knee point, to this knee point, to this knee point, so the increase in current I due to decrease in the load impedance ZL is more than the drop in the receiving end voltage. Therefore, your PL is increasing whereas VR is decreasing. Hence, the real power consumed by the load will increase. So, therefore, in this region, particular region, your PL will increase and VR will decrease because the increase in current is more as compared to the decrease in the receiving end voltage. Okay, so therefore the PL is increasing and VR is decreasing. So the maximum real power 1 per unit will be delivered at ZL equal to ZT. So this point at 1 per unit. So this point where ZL is equal to ZT. Once the operating point reaches the maximum power point or critical point or the knee point of the curve, any further decrease in load impedance to increase the load will result in further drop in the receiving end voltage, and simultaneously the real power consumed by the load will also decrease. So this is because up to the knee point the drop in the voltage is more than the increase in the line current, leading to the decrease in the real power. So here after the knee point, we can see here after this knee point, so the decrease in voltage is greater as compared to the increase in the current. So therefore what happens, your load power decreases in this region, the load power decreases again, falls. So you can see here after the knee point the load power is decreasing, simultaneously the VR is also decreasing. So you can see here the typical these are the characteristic PV curves plotted for different load factors, different load power factors. So now I can see this figure shows the PV curves for loads with different power factors. For 0.9 power factor lagging, for unity power factor, for 0.95 power factor leading, 0.9 power factor leading. So you can see here it can be observed from the figure that as the load power factor moves from lagging to leading, the knee point is shifted towards the higher real power and higher voltage. We can see here as the load power factor is from lagging to leading, the voltage profile is higher as compared to the lagging power factor. So this shows that the voltage stability improves as the power factor moves from lagging to leading loads. So this is one of the take home assignment. You can try it. So make a MATLAB program to draw the following PV curve. So by using those previous equations what we have derived, using those equations we can draw these curves for different load power factor using the MATLAB program. So it is easy, you can try it. Now this is the locus for, this is the curve of reactive power versus receiving end voltage. The load reactive power variation with respect to the receiving end voltage with load power being constant. load real power being constant is plotted. So here the load power factor, load real power is being constant. So this is constant, kept constant. Like you can see here, for different constant real power load, the plot has been done, the load reactive power versus the receiving end voltage. So the figure shows the variation of receiving end voltage with variation in the load reactive power for three different real power loads. Again, the locus of the knee point is marked here. The knee points are marked here. This is your locus of the knee point. On the curve left of the locus of the knee point, the reactive power and the voltage move in opposite direction. As we can see here, the slope in the left of the knee point is, the slope is negative. So therefore, you can see here very easily, the voltage and reactive power both move in the opposite direction. As we increase the reactive power injection, the voltage drops in this region, and as the reactive power injection decreases, the voltage increases. So that is what it is mentioned, that they move in opposite directions. So the curve on the, therefore this region is known as unstable region also. So therefore this region is unstable region. Unstable region. So the curve on the right of the locus of the knee point of the reactive power and voltage move in the same direction. We can see here the slope is positive here. So therefore slope is positive. So therefore as the reactive power injection increases, the voltage also increases. So they move in the same direction. Hence dq by dVr, or change in reactive power injection with respect to change in voltage, is positive, and therefore this region is stable region. So this region is stable region. Okay, so in the unstable region, even if the reactive power compensation is done through the shunt capacitance at the receiving end bus, the voltage of the receiving end bus will not improve. Even if we will do compensation here in the unstable region, even if we will make some shunt compensation for reactive power, still the voltage cannot improve in this region. So here another assignment, take home assignment. So we can make the MATLAB program to draw the following QV curves. Okay, this following QV curves, keeping the real load power constant, we can plot the load reactive power versus the receiving end. So one way of finding the voltage stability is to check the sensitivity of each bus voltage with respect to the reactive power injected at that bus. So this is the way we can do. So through the sensitivity method we can check the stability. If the sensitivity is positive, then it means the operating point is stable and is on the right side of the locus of the knee point. If it is negative, then it is on the left side and it is unstable. So it is very easy to find if we will check the sensitivity of voltage with respect to the reactive power injection. So this stable region and unstable region are only applicable to constant MVA load. So we should keep it in mind that this is only applicable to constant MVA loads, not for the constant current and constant impedance load. In case of constant impedance and constant current loads, the loads interact with the system and settle at a new operating point, as there is no requirement of constant MVA. Okay, so this is how it happens. So it adjusts, it settles in a new operating point when the loads are in the constant impedance and constant current loads. Okay, so let us do the static analysis first, and then we'll go for the dynamic analysis. In static analysis of voltage stability, the snapshots of the entire system at different instants is considered, and at each instant the snapshots of the entire system at different instants is considered, and at each instant the system is assumed to be in steady state. that is the rate of the changes of the dynamic variables are 0. So therefore it is assumed that the system is operating under steady state at a particular point. Hence, instead of conducting all the differential algebraic equations, only algebraic power balance equations are considered. Okay, so instead of considering all the differential algebraic equations, only algebraic equations are considered for this analysis. At each instant, whether the system is voltage stable or not, and also how far the system is from the instability, can be assessed through this sensitivity, through this static analysis. So there are two methods prescribed in the literature for assessing whether the system is voltage stable or not. There, one is sensitivity analysis and other one is your modal analysis method. So let us first talk about the sensitivity analysis. So the power balance equations are taken assuming that the system is in steady state. So now I can write the power balance equation. Let us say the system is having n number of buses. Assuming the bus number 1 is the slack bus, and the real power balance equation can be written in this way, that is Pgi minus Pdi as function of Vi minus Vi Vj Yij cos of theta I minus theta j minus alpha ij summation over j to n. So n is the total number of buses, and this equation indicates in fact your power injection equation. So this is your Pi. So this is Pi, power injection equation. So we know that power balance equation is Pgi minus Pdi is equal to Pi. So this is nothing but Pgi minus Pdi minus Pi equal to 0. So instead of Pi, we substituted the equation for power injection in terms of voltage at both the ends, voltage and the admittance matrix elements. So theta I is nothing but the angle of the voltage Vi, theta j is nothing but angle of voltage Vj, and alpha ij is the angle of the admittance matrix element Yij. The reactive power balance equations are taken at load buses. So as we know, in the load flow also we don't consider reactive power balance equations in generator buses, because in generator buses the reactive power is adjusted. So the reactive power balance equation is taken at the load buses only. Therefore, for I equal to Ng plus 1 to N. So these are the load buses for which the reactive power balance equation is considered. So again, if we'll write the reactive power balance equation, it will look like Qdi plus Vi Vj Yij sin theta I minus theta j minus alpha ij summation j from 1 to n. So here actually in fact, so this is from j equal to not 1 to okay, j equal to 1 to n is fine, it is correct. So we know this equation, this is reactive power injection is Qgi minus Qdi equal to Qi. So as we are considering the load buses, so Qgi will become 0 here. So therefore remaining terms are minus Qdi minus Qi equal to 0. So this is nothing but Qdi plus Qi equal to 0. So this is nothing but Qdi plus Qi equal to 0. So instead of Qi, we substituted the equation of Qi. So this is how we can write here, and here we can see next we can linearize this equation. So the linearized form of the above equations can be given as this. Already what we do in the load flow analysis also, the same thing we are doing here. After linearizing just by finding out the Jacobian matrix, so we can write this is your mismatch vector This is your correction vector. So these are all Jacobian elements. So now I can write this delta P delta Q equal to JP theta JPV JPV JQ theta and JQV delta theta delta V. So this is your then I can write this as delta P delta Q equal to nothing but J multiplied by delta theta delta V. So this is mismatch vector, this is correction vector. So the matrix J is the Jacobian matrix that is used in the Newton-Raphson load flow method. Already we know this how to calculate this Jacobian matrix. So the constant real power, that is delta P, is 0, hence from the above equation, because of the constant real power, because we are taking at a steady state point, so therefore we are considering the real power injection as constant, so your delta P will become 0. Hence from this equation from the above equation I can write this first equation, that is the first equation, delta P equal to Jp theta delta V plus Jpv delta theta. From there I can write delta theta equal to this. So from first equation will be delta P equal to Jp theta delta V plus Jpv, sorry, this is your delta theta, this is Jp theta delta theta Jpv delta V. So from this delta P equal to 0, if I'll substitute, I can find the equation for delta theta. So that will be nothing but minus of Jp theta inverse Jpv delta V. So similarly, if I'll substitute this delta theta equation in the second equation, that is delta Q equal to JQV minus JQ theta to JP theta inverse JPV into delta V. So now from this equation I can easily find the sensitivity of voltage with respect to power injection, change in reactive power injection. So I can write it delta V equal to JR inverse. So JR is nothing but JQV minus JQ theta into JP theta inverse JPV. So this is your JR. So if I'll take the inverse of JR, this will give me the sensitivity of voltage, change in voltage with respect to change in reactive power injection. So the diagonal elements of the JR inverse represents the sensitivity of the voltage with respect to the reactive power injected at that bus. So this is nothing but the slope of the QV curve, what we already discussed. So hence if VQ sensitivity of an ith bus is positive, then the system is voltage stable, and if it is negative, then the system is voltage unstable. So from this equation we can find very easily the sensitivity of voltage with respect to the change in reactive power injection. So let us now do the modal analysis. So voltage stability can also be estimated by eigenvalue analysis, or eigenvalues and eigenvectors of the matrix. So what JR inverse we have taken, if we can define JR inverse in terms of eigenvalues and eigenvectors, it is very easily we can do the modal analysis. So the matrix JR can be expressed in terms of right and left eigenvector matrices, that is phi and psi. As we can express this, so JR I can write psi, that is a diagonal matrix, a modal matrix, into phi. Psi is the left eigenvector and phi is the left eigenvector matrix and phi is the right eigenvector matrix. So if I'll take the JR inverse, the same equation I'll get except the modal matrix inverse, because if I'll take JR inverse, if I'll take JR inverse, I can find it as psi A phi inverse. So this is nothing but phi inverse, modal matrix inverse, psi inverse. So phi inverse is nothing but psi, modal matrix inverse, and psi inverse is phi. So I can write it as phi. So JR inverse is this. Okay. So therefore the diagonal matrix, just let me erase this. So I can write the diagonal matrix with eigenvalues along its diagonal elements, its diagonal matrix. So I can write delta V equal to JR inverse delta Q is nothing but it is equal to psi modal matrix inverse phi into delta Q. So if I'll multiply the right eigenvector in both the side, I can write phi delta V, that is equal to modal matrix inverse phi delta Q. So if I'll take small b equal to phi delta V and q small q equal to phi delta Q, there are, so I can write it as Vi equal to 1 by lambda I Qi, because modal matrix is a diagonal matrix. So now I can write the sensitivity, voltage sensitivity. So Vi is the ith bus modal voltage and Qi is the modal reactive power. So if the eigenvalue is positive, then the system is voltage stable. Okay, so the larger the eigenvalue with positive sign, better the stability, and if the eigenvalue has very small positive value, then it is very close to 0. That is the critical point or the knee point. So hence very close to the instability. If the eigenvalue is negative, then the system is voltage unstable. So obviously from this equation, this conclusion can be made that when the eigenvalue is negative, the system becomes unstable. So let us then do dynamic analysis. So the voltage stability of a system can also be assessed by the transient simulation over a period of time. So over a period of time, if we'll do the transient simulation, we can also find the voltage stability. So here the differential algebraic equations incomplete, it is considered as it is considered for the transient stability analysis, and it should be solved through the numerical methods to completely observe the interaction of the generators, static loads, dynamic loads, tap changing transformers, etc. So this is the differential algebraic equation. So x dot indicates your differential equation, that is the state equation of the system, and idq equal to h of xv and 0 equal to d. They are the algebraic equations. So this indicates the stator algebraic equation, and this is your network algebraic equation. So this is your stator algebraic equation, and this is your network algebraic equation. So both are, so the transient simulation should be done for different fault scenarios, and the system behavior should be observed for different fault scenarios, and if the system voltages are restored to acceptable values after fault clearing, then the system is voltage stable. If not, then the system is voltage unstable. So this is how we do the dynamic analysis. So we simulate, or we do the transient simulation analysis for different faults, and under different fault condition, after the fault clearing, if your voltage is retaining its acceptable value, then we say the system is voltage stable. If not, then it is voltage unstable. So the simulation needs to be done for few minutes because the time constant involved can be very small, like generator exciter, or very large like induction motors. So therefore the time period should be taken appropriately. For voltage stability assessment, The load modeling is important, hence both static and dynamic loads should be modeled appropriately. The reactive power compensating devices like the series or shunt capacitor and static power compensator should be included in the system model. So let us now consider the small disturbance analysis. So how we can do this small disturbance analysis for voltage stability assessment. So small disturbance analysis can also be used for voltage stability analysis. So the DAE is given in the above equation, what we have seen in the last slide. This is your differential algebraic equation. So now the H is in fact as it is merged with the state equations. So now where lambda in the equation is a constant representing the loading of the system and can be given as this. So lambda can be related to this, that is PD equal to, I can write PD equal to PDO into 1 plus lambda, and QD equal to QDO plus into 1 plus lambda. So PDO and QDO, they are nothing but they are the base loads, base real and reactive power loads. At the real and reactive power loads at all the load buses for the base case, the idea is to increase the loading factor lambda in steps. So here what we do, the lambda is increased in steps. At each step we find the eigenvalues of the linearized system, of this linearized system. Then after finding the eigenvalue we can say the system is stable or not for each load. So now by linearizing the above differential algebraic equation, just by linearizing we'll find this equation. So delta x dot is equal to delta f by delta x into delta x plus this is the matrix delta f by delta v delta f by delta theta multiplied with delta v delta theta, then plus delta f by delta u delta v. So these are evaluated at some equilibrium points. So they are evaluated at some equilibrium points. Similarly, the algebraic equation is also linearized. Now we just merging it just from this equation. If I'll this equation, if I'll find delta v delta theta in terms of delta x, then I can substitute in the first equation. I'll find delta x dot is this equation. So this matrix is known as the system Jacobian matrix, that is multiplied with delta x. So delta f delta f delta u. So this is your system Jacobian matrix. This is in fact different from the load flow Jacobian matrix. So now the system JSys is called the system Jacobian, and it is in fact different from the load flow Jacobian. So the eigenvalue of the system Jacobian for different loading conditions obtained by varying the loading factor lambda are computed. If one of the eigenvalue becomes 0 or a pair of complex conjugate eigenvalues are on the imaginary axis for a particular loading factor lambda, then the load corresponding to the loading factor lambda is a critical load at which the system becomes voltage unstable. If a complex conjugate pair of eigenvalues are on the imaginary axis, then that operating point is called half bifurcation point. If one of the eigenvalue is on the origin, then the operating point is called the saddle node point. The saddle node bifurcation point represents the knee point. Half bifurcation point occurs at a load which is less than the load at which the saddle node bifurcation point occurs. Hence, due to dynamics involved in the system can become voltage unstable even before the operating point reaches the knee point. So this is all about your voltage stability, and with this lecture we are concluding the whole course of power system dynamics and control, and these are the references I took during my lecture. So first reference is the power system stability and control. It's a reference book by P. Kundur and published by McGraw-Hill in 1994, and the second one is also a book. It is The Power System Dynamics and Stability, it is by P.W. Sawyer and M.A. Pai, 2018 edition. And third one is the NPTEL lecture notes by Professor B. Kalyan Kumar, IIT Madras. So thank you very much. With this, I conclude the whole syllabus of power system dynamics and control, that is E549. Thank you very much.